So we found that if p is prime and p does not divide a, then the least k, where a to the power k is congruent to 1 mod p, is a divisor of p minus 1. But what if p isn't prime? We'll have to assume that the greatest common divisor of a and p is still 1. So, as before, we'll take a to be something between 1 and p, and let k be the least value for which a to the power k is congruent to 1 mod p. Again, as before, this means that if we take a look at the powers of a, eventually there is some least value congruent to 1, where all the preceding values are distinct. But what values could we get? So to start off with, a to the power I can never be congruent to 0 mod p. To prove it, let's take advantage of our assumption that the greatest common divisor of a and p is 1. This means that a has a multiplicative inverse, which we'll designate this way. Remember, this is not an exponent in the usual sense. This is not 1 divided by a, because you can't do division mod n, but this is an easy way to designate the multiplicative inverse of a. If a to the power I is congruent to 0 mod p, then we can multiply by a power of a inverse to get a congruent to 0. But if a is between 1 and p, this can't be true. So the first strategy in number theory is to consider the primes. The second strategy is to consider the relative primes. Could a to the power I be congruent to b where b is also relatively prime to p? From our proof for the case where p is prime, we found that it might occur, but it might not. So this will be harder to analyze because sometimes it is true and sometimes it isn't. So we'll use an important strategy in math and in life. Ignore it for now. How about a to the power I being congruent to b where the greatest common divisor of b and p is something other than 1? So if a to the I is congruent to b, then p has to divide a to the I minus b. Now let q be a prime factor of d. Since d divides a to the I, then q must also divide a to the I. But since q is prime, q must divide a. But since q is a divisor of d, which is a divisor of p, then q divides p as well, until the greatest common divisor of a and p is greater than or equal to q, which is not 1. But we assume the greatest common divisor of a and p was 1, so this can't happen. Consequently, if the greatest common divisor of a and p is 1, and the greatest common divisor of b and p isn't 1, then a to the k can't be congruent to b mod p. And a useful strategy, consider the contrapositive. So we'll negate the consequent and the antecedent and switch them. If the greatest common divisor of a and p is 1, if a to the k is congruent to b mod p, then the greatest common divisor of b and p is 1 as well. This means that a to the power k can only be congruent to numbers relatively prime to the modulus. And it's useful to check for consistency. If p was prime, then a to the k had to be one of the values from 1 to p minus 1. But if p is prime, these are all relatively prime to p. So the result holds whether or not p is actually prime. So at this point, we'll introduce what is sometimes called the most important function in number theory, known as the Euler phi function. This is also called the Euler totient, or just the totient. Phi of n is a number of numbers less than n that are relatively prime to it. So let k be the least positive value for which a to the k is congruent to 1 mod p. Our theorem says that the values of a squared, and so on must be one of the phi of p numbers less than p that are relatively prime to p. As before, if this includes all the numbers, then that least power is just phi of p. If not, let r be a number relatively prime to p not included among our list, and we'll consider what happens when we multiply the powers by r. Again, as before, these must be distinct from each other and from the powers of a. Moreover, they must also be among the numbers relatively prime to p. We'll prove this as follows. Do this as a homework problem. Now again, if this includes all the values, then 2k is phi of p. If not, let s be a value relatively prime to p that is not among the values, so, and lather, rinse, repeat, gives us what's known as the Euler-Fermat theorem. Let the greatest common divisor of a and p be 1. The least value k for which a to the k is congruent to 1 mod p is a divisor of phi of p. This will help us solve certain types of equations. For example, say we want to solve 3 to the x is congruent to 1 mod 20. Now we could try values of x 1, 2, 3, and so on, but if the smallest power is a large number, this would take a long time. Instead, we'll use our theorem. The least power k, where 3 to the power k is congruent to 1 mod 20, is a divisor of phi of 20. Of course, this does require us to find phi of 20. So we note that the numbers less than 20 that are relatively prime to it are. So phi of 20 is the number of numbers that are relatively prime, which is going to be 8. So x is a divisor of 8. It's either 1, 2, 4, or 8. And we find that 3 to the power 4 is congruent to 1 mod 20. So far, so good, but now let's consider something like 8 to the x congruent to 1 mod 35. The numbers less than 35 that are relatively prime to 35 are, well, actually, there's a fairly long list. So is there an easier way to find phi of n? We'll take a look at that next.